Good morning, participants. We are starting day 3 of ATAL sponsored FDP from KLS Gupta Institute of Technology. I welcome you all for this session by Dr. Maruti Tamrakar. It is indeed a very important talk for us, and I thank Maruti sir for accepting our invitation and delivering a talk on uh, talk on antennas during this FDP. It is my privilege to introduce Dr. Maruti Tamrakar. Dr. Maruti has received his PhD degree from Vellore Institute of Technology, Chennai campus, Tamil Nadu, from for research work on metamaterial-based antennas. He obtained MTech degree in RF and microwave engineering from the Indian Institute of Technology, Kharagpur, West Bengal. He started his industry with HCL Technologies Limited India in 2010 as an antenna engineer, and currently he is working in Intel Technology India Private Limited as antenna engineer since 2018. His current industry work includes small antennas for laptop, tablet and mobile phones, miniaturized antennas, and EMI EMC in systems. He also worked on base station antenna, multi-band router, access point MIMO antenna, and wireless charging. With this introduction, I thank once again, sir, for accepting our invitation, and I request him to start his session. Thank you.
Yeah. Thank you, sir, for inviting me on this EPD. Yeah, it's like pleasure for me to give the talk and share my experience with the faculties for their growth and for growth of the student. So let me share. Yeah. So I covered topic today. Hope you can see my screen.
Yes, sir.
Yeah, thank you. So today I'll deliver the talk on 5G antenna design and system and its integration. So let me go to the wireless system, especially cellular. If you see, we started from 1G on 1980, and then one second. Yeah. Then we have the only voice-based communication during that time. When we moved to the 2G, we basically started text message texting from the 2G onwards, and from the 3G, if you see, we started browsing using the browsing and all. So nearly year of 2000, we started browsing internet, and we started internet access from 4G onwards. Basically we started using the video calls and the lots of bandwidth we utilizing. So when we are moving from 1G 2G 3G 4G, what basically we are doing, we are developing more and more application. Same time we are increasing the bandwidth and the speed requirement. So what will come on the 5G side? So obviously 5G, again the bandwidth demand and the need is very high. So like 3.5G or LT band, we are in 42 Mbps or 2000 Mbps, but in range of 5G will go even 10 times higher, approx 10 times higher will go on the 5G. So basically we are increasing the band utilization. So, what is the application and the way how to see the 5G? So, 5G, when I see, basically first is data rate. The data rate is very high. 10 Gbps is the target, and low latency. So, when we are switching from one network to another network, or while walking, the switching within the network and all should be less than 1 millisecond, which is higher today. So and carrier aggregation. So carrier aggregation target is up to 8 CA. CA means carrier aggregation, and the application will come towards the millimeter wave. So another new thing which is going to come with 5G is dynamic beamforming. So beamforming we know, but here is the utilization is going to come heavily with the 5G. And so altogether what we are doing, we are improving the throughput 10 times, we are reducing the latency, we are going to have the more density, spectrum efficiency. So it altogether, if you see the as a architect, there is lots of improvement going to happen with the 5G. So the application is very vast. If you see, we can work on the smart city side. It is for the self communication, self-driving car in the industry. The application is very vast. When I see the 5G, it's not only restrict to our mobile phone or the laptop uses. It will go beyond that, and for the some application may go to IoT and the machine to machine communication. So I see a very vast application and very vast adoption throughout the world in the 5G, for the 5G actually. So let's talk about the spectrum. So when I see the spectrum, see, basically, we have seen in the first slide, we are moving from 1G to 5G. So bandwidth is increasing. So where we'll get the bandwidth? Bandwidth will come from the this spectrum. Earlier, we were in range of 600, 700 megahertz only in the initial days. But today we are using a vast band. We are using from approx 600 up to 6 gigahertz in the cellular band. Same time, we are also using the millimeter wave side. In the coming slide, I'll give you exact frequency bands also, which are the we are using. So here another example of comparing with 3G and LTE and 5G. You can see the green line. The green bar is the we are using only small band of frequency in 3G. So 4G, again some band of frequency is increased on the 600 megahertz, 700 megahertz range also, and same time here is to 2.5 to 2.7 gigahertz range also. But in 5G, you can see the frequency band requirements is increased so much, and it's up to 6 gigahertz. Similarly, we have something on the millimeter wave. We will see that. So see now, in practical, if you see, we are not going to utilize all band at a time. It is like a region based. Like Europe, they will use some other frequency. China, they will use some other frequency. In India, we are going to use some other frequency, and in Korea. So region based, the frequency demand and the use cases are different. But in general, as a researcher or as a design engineer, we look for the do the research work or design work in for the common application. I cannot say I am doing only for this particular reason. It's very we should not restrict it. So we should go for the beyond our reason, and we should look for the all possible frequency band. So let me this was the introduction for 5G. Let me move toward the MIMO. You may aware already, but let me give in my aspect how I see the MIMO. So when I see the MIMO, we know it's a multiple input, multiple output. So multiple input means multiple output means the two antenna. If I take two antenna alone, that can also work as a MIMO. So two antennas, both will be transmitting and both are receiving. So it is a 2 cross 2 MIMO. So here 2 cross 2 MIMO, and I see the big benefit. I see the big benefit. We can see the MIMO in two ways. One is the diversity technique, and another is the multiplexing techniques. So when we use this MIMO for the diversity technique, I'm basically improving the diversity gain and the reliability. In case of multiplexing, which comes with the distance, we have to place our antennas little far away. So when we use the multiplexing technique with the MIMO, basically I'm increasing the data rate. So this what happen in general, it will directly help me to improve in the signal to noise ratio. So the MIMO application today in the Wi-Fi or the 5G we use extensively. Like become our regular job to implement the MIMO in every wireless systems. So let me move to the design aspect of the antenna for the laptop and phone. So if you see, we have in era of 2G and 3G, we have seen the VEEP antenna. Let me put marker. Yeah, thank you. So when we see this kind of external antenna on the phone, we have seen earlier in the starting days of phone development. So this is the monopole antenna, and some of the we call as a VEEP antenna also. And there is an inside that structure we see the helix shape, which gives us the miniaturization for the monopole or the VEEP. And same time, as we progress on 3G, we have seen the P5 structure, and this is the P5 structure on the phone. As we move forward for the miniaturization, and the like you can see, it's taking a large area for the antenna. So for the miniaturization, we went and we can see the inverted F antenna. So inverted F antenna, the area occupied by the antenna is less, and then there are antennas with the monopole printed on the body. Now today generation phone, if you see, you see this kind of structure. We will see in coming slide what kind of antenna is this and how it looks like basically. So these are the growth you will see in our mobile phone or the laptop, generation to generation in and antenna, how antenna evolved. So this we have discussed early, and for 1G we had only voice call, 2G it came with text, 3G we started browsing, 4G we started doing the video call, but 5G will have many more application coming up. So let's think about design aspect. So we know dipole antenna, it's a lambda by 2 structure, and we know that we can convert this dipole antenna in the monopole structure. So when we have monopole structure, we'll generally have the reference ground, and that is way we can half make the structure half shape. Suppose this is the approx 50 mm length, so we can design our antenna in 25 mm length. So this is where it start actually. So we are most of the time we prefer the monopole shape. So here I'm not going in very depth how antenna radiates, why antenna radiates and how it works. So basically we have to give the sinusoidal signal, and sinusoidal signal will help us the radiation coming out of the antenna. So if somebody wants, we can see in question session if in depth people want to discuss. So in monopole, for the further miniaturization, what we do, we apply the bending. So when we apply the bending, we're trying to save the physical space. So this is the L bending. So same time you have seen that this kind of shape, either a straight line or the L bending, it will not offer us the bandwidth. So how to achieve the bandwidth? So to achieve the bandwidth, what we do, we create a monopole shorted line. This is a lambda by 4 shorted line, and we do the coupling. So the coupling is happening through this strip. We can call it exciting feed. So from the feed, there is a capacitive coupling, and this capacitive coupling, so you can see there are two lengths. One length is lambda by 4, and which is longer lambda by 4, which will resonate for f1, let's say f1 frequency. For the smaller strip, again this is the lambda by 4 for the f2, which is the higher frequency. So basically using this, I'll get the two frequency bands. From the above image, I'm getting the one frequency band, but for the middle image, I'm getting the two frequency band. And because of the coupling, I'll get the better bandwidth compared to the first one. Similarly, another technique is that lambda by 4 loop antenna. So generally loop antenna we know with the lambda length and the or lambda by 2 length. But nowadays we are doing the antenna design with lambda by 4 loop length. So basically it offers even wider bandwidth if we design it properly. So this is how antenna we implement. Suppose this is the body of the system. It can be a laptop, it can be a mobile phone. We offer the small gap. So this gap is the non-metal gap, or we call it as a plastic region or the substrate region, which is the non-metal part. And because the radiation, we know the electric field will start from positive or and it will end to the ground. So when as we go very close to the ground plane, our efficiency or antenna performance drops heavily. So we have to maintain certain gap. In theoretically, it is lambda by 20, but lambda by 10. Lambda by 10, yes. So but we cannot get very privileged to have very large plastic area for better efficiency and better performance. So we make trade off in terms of overall dimension, because you see, if I'm offering this space as a free space, that means it will account for the overall antenna dimension. So if I give the larger plastic area, yes, my antenna performance will be good, but same time my antenna size will become higher. So we compromise and we set up at the threshold value or the trade-off we do, so we can maintain our antenna performance, same time we'll have the smaller dimension. So two ways we can do. You can see that a same antenna is implemented in two different way. These are the real-time example. You can see these are the monopole antennas, and this one point will use as a feed, and different shapes you can see based on the structure of the your device. It can be a mobile phone, it can be a laptop, or any other small devices you can use. So based on device, we can implement these antennas on the profile of the device basically. So this is the flat structure you can see, but some of the structure we can see it is on orthogonal space there, horizontal and vertical space they are using. Some of the space are curved. So these are the trends we use to utilize the device body shape and the space to develop our antennas. These are the three techniques for the implementation. We use the FPC. So FPC is the flexible PCB basically, and you can see why we use the FPC. You can see some of the space are the curved space, some of the space are the 90-degree band. So we cannot use our FR4 0.8 mm 1.6 thickness. So those which we use in college days, in our institute, generally it's very difficult to adopt it. We generally go for the FPC for the utilizing the surface of our devices and antenna integration. Same time, these are the metal stamp. This is the metal piece only. It can be aluminum and other material, conducting material. It can be a brass or a copper. So basically, we do this stamping and we just provide a direct physical connection with the source feed, or through the cable or some connector. Another is the LDS, so laser direct structuring. These are the little costly technique. The cost of manufacturing is high. So you can see that on the back cover of the mobile phone, directly this copper are printed on the body, so it save loss of the space within the device. So what are the parameters we should look on the antenna side? So here I'm believing that all of them are faculty, so I'm not going in very much basic parameters. I am assuming that you all are aware. So let me go here. So the what are the criteria, what are the specification or the constraint for the antenna? So first constraint comes from the peak gain. We say that the peak gain should not go beyond 5 dB. So we do not want more than 5 dB. What is meaning of this? See, if you see more higher gain means it will become directive. Our antenna is a directive, but actual in scenario we do not want directive antenna. We want omnidirectional antenna. So if I like here at the laptop example, if I my laptop orientation can be in any side. So my connectivity, or I do not want any line of sight for my wireless connectivity. So my radiation pattern from my antenna also has to be omnidirectional to fulfill that. Correct. Say next important parameter. So when we say my gain is more than 5 dB, that means I am direct. My antenna is directive, and I cannot have the omnidirectional pattern. So the constraint is that it cannot be more than 5 dB. That is the limit. Another parameter is efficiency. Efficiency is very critical parameter, and we see as we discussed in a previous slide, as our antenna pattern, if it is very close to ground plane, we see the heavy drop in the efficiency. So, but same time, I cannot increase my overall antenna dimension. You can see when you are holding your phone or something, there are many antennas. So, how to fit antennas? There is a size constraint. There is a dimension constraint. We do not have the space. So, efficiency will drop heavily. So, what is the threshold value which we feel? So, 50% is the threshold value. We try to get the at least 50% efficiency level from our antenna in a system. Impedance matching, obviously we follow the 50 ohm, which is the standard. Same time, we do active measurements with the system. When I say active measurements, see, the first three parameters are we call as a passive measurement. What is passive measurement? I just need a standalone antenna or antenna fitted on the system, integrated on the system. So I do not need actual power coming from the my Wi-Fi modem or the 5G modem. But when I do the total isotropic sensitivity (TIS) or total radiated power, I do the active measurement where my system, full system is on. I'm getting RF power from my Wi-Fi modem or from my 5G modem. So there we calculate in real time environment. Just for example, I'm giving, suppose my Wi-Fi modem is giving 0 dBm power, and my antenna has gain of let's say 3 dBi. So overall, what I'm transmitting 3 dBm of power out of my system. So that will be my total radiated power. Similarly, while receiving, I will see that suppose based on efficiency, my efficiency is minus 3 dB. So assume that I'm receiving minus 50 dBm power at minus 50 dBm of power at my antenna end. So my total power is how much? My power is become minus 53 dBm. 3 dB loss will happen because of efficiency. So and there are many other losses within the system, like because of the filter, because of the transmission line insertion loss. So altogether, what is my total sensitivity, total isotopic sensitivity? So these two parameters we do the active testing. So first three is passive, and the fourth one is the active. Last parameter which is important is the isolation. We have to see the isolation between each antenna. Suppose you have four antennas within your system, we have to check the isolation. What is the isolation among this all four antennas? Because this will create a problem, especially for the MIMO feature. Like we have seen that MIMO has some advantage. If we do not have the isolation, we will lose the MIMO property here. We cannot enable it. So these are the five parameters we look in the antenna from the antenna side to implement in a system. This is the small theory we follow while designing. You see, we can do the either we can do the very narrow band design, or we can do the wide band design. So when we are doing the narrow band design, you can achieve the very good return loss or the reflection coefficient of very high reflection coefficient you can achieve, but it will be a narrow band. But when you target very high bandwidth, generally we cannot achieve the very good return loss or reflection coefficient. So we always target for the 6 dB environment. So minus 6 dB return loss or reflection coefficient, this is our general target in our application, because we look for the bandwidth in our design. In our system, mobile phone or a laptop, we target to have the minus 6 dB reflection coefficient, not exactly 10 dB or 8 dB. And I have seen in the industry, like we look for the minus 10 dB return loss. If we can achieve, yes, it is always best, but sometimes it's become impossible because the bandwidth requirement. So 80 to 90% cases I have seen that we are settling at the minus 6 dB return loss level. One more reason of for minus 6 dB settling at the minus 6 dB is that I believe it's a power requirement, current requirement. Suppose when you're working for very high power, like 200 kilowatt or the 200 watt or very high power, then your amount of reflected power, if it is 6 dB, then it will be very high. So generally when we are working on the very high power 200 watt or beyond, generally we look for the minus 15 dB of return loss or the reflection coefficient. And but when we are working at the low power, so low power means if my return loss or reflection coefficient is minus 6 dB, sometimes it become acceptable because the amount of reflected current or the power is less. So I believe when we are working on low power, minus 6 dB may be acceptable, but when you are working on very high power, like beyond 200 watt or something, the requirement will be minus 15 dB. So these are the trend I see, trade off between the current. This is the another example of the design in monopole. These are the monopole antennas. The small white line, this is I captured from one of the paper. So you can see this white line. This is nothing but a slot structure. The slot means the cutout in the metal. The whole area, the whole green area is the metal part, and this yellow area is the again metal part. And here we use some of the matching components. You can see there are one, two, three. So three matching component here and three matching component in this direction. So we use this matching circuit component to achieve the bandwidth. If I do not use, you can see we get the narrow band. When we use this matching components, we can improve the bandwidth. Again, this is example of same what we have seen here. We are controlling the quality factor of the design. So you can see from the small band we are converting in the very wide band for the and settling at the approximately return loss of 6 dB. This is what we follow. So we use this matching component to control the bandwidth or the frequency band requirement. Here using this component, I'm not doing the frequency shift. I'm not moving from one frequency to another frequency. Rather than we are just trying to improve the bandwidth at same resonance frequency. This is the one example you see, this is the simply monopole antenna. You can see very small monopole antenna for Bluetooth, and same the Bluetooth will work for 2.4 and the GPS will work for the 1.5. So you can see it's little longer length compared to the this one, and which shows that because these all are wavelength dependent, lambda by 4 line. Similarly, one more example, if you see, these are the another inverted F antenna we see here in this app, in this mobile phone. You can see. See, in 5G system now, these are the example we have seen in 5G system today. What are the wireless and what are the antennas? How many antennas we required? So we need so many antennas with today's wireless application. We need for 5G. We need one we call as a main antenna, which will cover GSM, CDMA, LTE, and these are the frequency range 617 to 6,000 megahertz. There is for 5G diverse, we call as a diversity or aux antenna. So diversity antenna again have same frequency band. MIMO. So 5G MIMO has two antennas. So this will cover 1.8 to 6 gigahertz. So first three, and the millimeter wave. So first four rows, what we see is the for the 5G application. So 5G, you see when we see the 5G, how many antennas? One, two, 4 and 6, total 6 antennas minimum required in a system. 6 antennas for 5G application. Similarly, when we go for the W line or Wi-Fi, we need two antennas. So it will combine with Bluetooth also. So 2.4 to 2.5, and then 5.1 to 5.8. Similarly, new in this Wi-Fi, actually new band is added. We are calling as a Wi-Fi 6E. So Wi-Fi 6E, this is the new band added in the 6 gigahertz range, and which will basically going to give us the more bandwidth and more data rate. There is another requirement in a system is NFC, and then GNSS or GPS and RFID. So these are the current requirement in a system, in a laptop or mobile phone. We need this much, this many antennas or this many wireless communication in a system. So let's go for the placement. Now these are the antenna, where we place the antenna. So when you see this is the screen of our laptop. So generally the top area, which is the non-screen area, we call it as bezel. So bezel area we utilize to place the antenna, and this screen, the active area, basically where we see our work. And so active area is the basically a metal area, and we want our antenna on non-metal place on the somewhere on the plastic region. So the reason of this area, non-active area, is the plastic, and we place our antennas there. So on the top side or left and right side or the bottom side, four possible areas are there for the antenna placement. Generally here your dimension you are seeing 70 cross 13, 75 to 13, but today's if you see the dimension is keep reducing. And every system will come with very narrow space offered for the this bezel actually. So with as time progressing, we are seeing this dimension, the 13 dimension, is reducing further and further. Another example of antenna placement, if you see, we can place Wi-Fi and MIMO on the top of the lead, and the 5G is coming near the keyboard area. So we are placing a 5G antenna near the keyboard area actually. These are the one example how we develop antenna. These are the practical antenna, and this is the simulation. So this is the example I took from the CST website. So it is not my design. I took from the example from CST. So here you can see that we try to develop exact model in a simulation tool. And in the simulation tool, we develop all equivalent. These are the components, equivalent circuit, and try to have the similar environment as our practical, so we'll get the close matching in the simulation and measurement. So this is the WFL or U.FL cable and connectors we use. These are the miniaturized or is very small RF connectors which we use in the system. Not we do not use the SMA or N type connectors. So what are the things matters in antenna design and the placement and assay altogether? One thing is matter is antenna size. So now today antenna needs 600 megas to 6 gigahertz range. So we know that our antenna designs are the wavelength dependent. So size matters a lot. Size matters a lot. Second parameter we have to always see is the isolation. We have to see that isolation should meet at least 15 dB distance. Second is that interference. See, antenna may interfere with the other system components. We have the clock or other memory or many other like high speed running components within a system. So those components may interfere with the antenna. Another one is that we have to look for the device mechanical dimension. So how it is, whether it's how much space we have, how much body shape, it is curvy shape or the flat shape, and how it is a metal, non-metal, many other mechanical constraint we have to see in the keyboard area or the screen area both. Same time FCC SAR regulation is become important. So we have to look whether my antenna design or SAR limitation is meeting or not. Same time we have the OTA, open air testing basically, and TRPTIS. So some of the active TRPTIS we have seen: total radiated power, total isotopic sensitivity. So we have to look that it is meeting the this requirement for certification, and final comes as a cost. So altogether, as a engineer, this parameters matters to us in terms of design and implementation. So, Sar, yes, in mobile phone, we have seen, like you may have seen earlier, but nowadays, since the number of antennas are increasing in the laptop, this has become very much important factor for the like antenna design in the laptop. So this will not only seen in mobile phone. This we are going to see in the laptop also. This is the one example I took from the Google search, and you can see that how designs are complex, how one laptop inside looks like and mobile phone looks like. So you will, if you see here is the 5G antenna and the Wi-Fi antenna, how close they are placed. How close they are placed and how tiny the antenna. It's you will not see the much space offered, and this PCB area has the lots of ground plane or lots of the conductor area. So antenna is coming very close to the conductor area. So as we discussed earlier, if antenna is coming close to the ground plane, we are going to lose the efficiency. So antenna performance will affect a lot. And these are the few cables you can see. These are the WFL or U.FL cable we have seen in previous slide. So these are the connectors, tiny connectors we use actually. So today we need lots of antenna, and lots of research work is also required from for these antennas to fit in a very small space, very compact space. Same time we need to improve the overall bandwidth performance for the each antennas, so that the challenges are very high. Yeah, thank you. Any question, please let me know.
Friends, if you have questions, you can post in the chat box or you can unmute and ask.
Sir, good morning, Maruti
Yeah,
sir.
yeah, good morning.
Sir, thank you for this very well framed presentation. One query I'm having is Intel providing some kind of internship or research opportunities for postgraduate or undergraduate students in your labs?
Yes,
Because when we
they
are designing antennas in
yes,
colleges, as you mentioned, we are using FR4 substrate or non-flexible substrate. But as per your slides, in practical antenna design or implementation, we require flexible substrates. I don't know which
yeah,
substrate was used, but it is required. So some gap is there between academics and industry, as I can see.
yeah.
And one more thing, sir, along with this question, I would like to ask you, that can you please repeat the explanation for the reduction in efficiency when the antenna and the metal means ground plane you are talking about, or if you
Yes,
can repeat that concept, please.
sure. So first regarding internship, yes, Intel provide the internship to the students for BTech, B and MTech, and even PhD also they provide. So there are proper channel. You can apply in career site also, and they recruit from the campus. So there are multiple ways for internship. One rule which I know, I'm not like from the recruitment side. I'm more on technical side only, but there is possibility of applying on the career side, and if you want I can guide you also, and for your you or your student anyone, and there are career site where we can apply directly there. Only one rule which is must, which I'm aware from the recruitment site, is that it is ongoing. Suppose somebody has passed out, they cannot apply for internship, they can apply for full time. But somebody is ongoing, yes, any from any institute, they can apply for internship. So it should be ongoing. That is the criteria for internship. Let me go to the second question, where I was talking about the efficiency requirement. So you see, when we are doing the banding and all, see, we know one thing, in our basic electromagnetics, the electric field start from the positive and it will end to the negative, right? Or ground. So basically when and here in antenna we want radiation out of our system. So when we want antenna to be radiation to be out of the system, we do not want to see radiating part close to the ground or the conductor area. See, this is the low impedance area or current is high. This is the point high impedance area and the voltage is high. And voltage we know it is related to electric field. So E is equal to V by L. So here voltage will be high and electric field will be high. So mean radiation where electric field releases, electric field will release from the this one. If it is very close to ground plane, it will terminate to the ground plane or the any conductor path. So what will happen? Instead of your radiation going out in the word, it will terminate here. So if your fields are terminated here, means what you are doing, you are losing your efficiency. We are not getting the good efficiency. And overall, suppose what is mean of 50% efficiency? Suppose I am giving 0 dBm power, in the air I'll receive only minus 3 dBm of power, so 3 dB is lost. So we do not want to lose the power. So we have to design such a way that we get the more efficient antenna. So you can see the two example. So same antenna has placed in two different ways, correct? Same design, same concept, but there is a chance that in one antenna I may get poor efficiency, and another antenna I get the better efficiency. The reason is that how close we are coming to the ground plane, correct?
Sir, but ground plane is on the other side of the substrate, na? Means it is below the substrate. I can see from this diagram.
Mm-hmm.
So it is
Mm-hmm.
always there.
Yeah,
The
it is
feed line
always
is
there.
moving. Yeah. So
Yeah.
how you are saying that it is away from the metal part or radiator? You can see there
See
is a
the
radiator in your diagram, in the left hand side diagram, and there is
hmm,
a feed line that is dark blue in color,
hmm,
and we
hmm.
are feeding it, I think, using probe feed, and the ground plane is
Microchip.
at the
Ah,
bottom.
hmm.
So how
Yeah.
ground plane is away? It is always there below, beneath the substrate.
Yeah, it is there. It is there. See, we need, this is a transmission line. This is a 50 ohm transmission line, and we need a ground plane for the 50 ohm transmission line. We can, it is a must, correct? So here the gap from this point till this point, there is a gap, correct? From the ground to the antenna part. So the this gap I am talking. So let me explain you. Uh, yeah. So I'm talking about this gap basically. So this gap is critical for me. Suppose from this ground plane to the radiator, if this gap is more than, in theoretically it is lambda by 10. So when it is lambda by 10, I'll get the very good efficiency. But as we have seen in the some of the actual system, we do not get this much luxury. We do not have the this much free space available in our systems, in compact and complex systems. So we have to bring down this gap down actually. And basically today if you see we are close to lambda by 20 or below, or let me say for wi-fi, I can tell you for wi-fi. So for wi-fi it is less than 4 distance. In theories and in our textbook we will see it is a 6 to 10 gap, this arrow. But today when we are implementing, it is less than 4 space. So here the efficiency play a big role here.
Okay, sir, I got your point. Thank you. It was a very, very informative session, and I would request you to kindly share your email ID. My students are also working on MIMO, so we can collaborate, and even we can go for patent filing and all. If you can
Yeah,
kindly
sure.
share your email ID.
Sure, I can share, no problem. Uh, maybe
Any few questions in
through,
the chat box.
yeah. Please come through Datta sir, Doctor sir, Datta sir. So it will be a proper channel instead of sharing here.
Yes, sir.
Okay. Yeah. Thank you.
Yeah. Sir, I
Any
can see
other?
questions in the chat box. Swapnil sir wants to know about
Huh,
transmitter antennas for 5G,
huh.
particularly how it will be mounted and placed.
Okay.
That's the question.
Yeah. So here when we see the antennas basically transmitting and the receiving, I do not see as transmitting and receiving as a separate antenna. Only aspect will be the SAR. So when we have the transmitting antenna, we have to look for the SAR. If it is receiving antenna, we are not bothered about the SAR. So suppose this is the laptop environment, and this is the where my hands comes in picture. This is the where my hands come in picture. So if I am placing my transmitting antenna in this location, then I have to worry about SAR. But somehow if I place my transmitting antenna on the nearby lead this region, top region, then I do not worry about the SAR. So very easy way is that I can place my transmitting antenna on the top of the lead and the receiving antenna on the bottom side. So it will solve my SAR problem. I will not see the SAR problem. Same time, if I ignore the SAR and I look for the in general, then I do not differentiate between transmitting and receiving. It will be perfect location in terms of performance, like better efficiency, meeting the spec. So I look on that angle rather than looking on the transmitting and receiving.
Sorry, sir. I wanted to ask the question that in case of 4G, we have this transmitter tower mounted in
Oh,
nearby
tower.
areas. They are
Okay.
serving
Okay.
the cells. So how it
Hmm.
will be mounted on the towers? That kind of antennas I was asking about.
Okay, you are talking about base station antenna basically.
Yes,
So
base
when I
station
look,
antenna. Yes, sir.
so when I look for the base station antenna, it will be same mounting only. Mounting will not change. They are going to use the same tower for the placement, but instead of having it will be more a beam forming. Now what will happen? Uh, like for the single tower, there are three antennas for one application. One antenna will cover 120 degree, so they need three antennas to cover 360 degree. Okay, so for the one frequency, one application, three antennas are required in a tower, in a single tower. So the mounting and the of the 5G antenna will are going to be similar, but today for 4G it is a single beam which is covered 120 degree. 120 degree for the 10 dB bandwidth. Like when we talk about the beam width, here in base station it is a 10 dB down bandwidth beam width, not the 3 dB beam width. So 3 dB beam width is generally 65 degree, but 10 dB beam width is 120 degree. But in case of 5G, it will be more like beam forming. There will be dynamic beam forming, and the beam width will be close to the one side evolution of vertical side. It will be approx 7 degree to 10 degree, and the horizontal side it will be 20 degree or even less. So it will be more like a beam forming will be there, and again there will be three different antennas will come in a single tower like 4G only.
Okay, sir. Thank you, sir.
Yeah,
Maruti sir, I have one more question. Sorry, I interrupted you once again.
no problem.
What are the industry applications of UWB MIMO antennas?
Yeah,
Ultra
definitely.
wide.
You may have heard that like yes, I see like when you go for the general UW, when you say UW word, first comes in mind at 3.1 gigahertz to 10.6 gigahertz. That comes in my mind or anybody's mind. Correct. But here we have to look on the frequency pointer. Suppose you want to target the today's frequency or the upcoming frequency. I believe we still this UWB frequency has to shift on the today's requirement. Now, if you talk about only UWB, which is 3.1 to 10.6, I'm not seeing much application today actually. Like I'm not aware. There may be people are working, but I'm not aware. So if you to say that, see, one band, suppose I'm able to get 600 megahertz to 6 gigahertz, even I will call that as a UW, because that is also a very wide band, more than 100% bandwidth as a theory. So I'll also call that as a UWB. So which one you are talking, 3.1 to 10.6 or in other way?
Yes, sir. 3.1 to 10.6, which is regularized by FCC. And I
Yeah.
just wanted
So
to know the application of ultra wideband MIMO antennas. Ultra wideband antennas, their application I know. But what is the why we combine generally ultra wideband with MIMO for which applications in industry?
I'm not seeing much application personally. I'm not aware because maybe I did not get time to spend on it. I my knowledge is limited on that side. But in general, MIMO, in general, I say as a theoretically when we talk about MIMO, we use MIMO to improve the signal to noise ratio. Overall application, I'm saying. See, generally, what is the main purpose? While transmitting, we have more control. You can transmit 0 dBm power, you can transmit 30 dBm power on any power, but while receiving it will become a constraint. So the receiver sensitivity for the GSM phones and all, like phone, it is minus close to minus 90 dBm. So for the for GPS or the GPRS on, it will go even lower, minus 120, minus 130 dBm. So the sensitivity level is different. So by applying the MIMO technique, we try to boost the signal to noise ratio so we can improve the reception of the signal. So that is the very general application I see. And now you can apply this technique in like in real time environment anywhere. But personally, my knowledge is limited. Exact application, I'm not sure.
Okay, sir. Thank you very much. Thank you, sir.
Maruti sir, there is one question by Mr. Anup. 15 dB isolation between two adjacent antennas. Can you elaborate a bit?
Yeah. So you have seen that we are looking for the in MIMO application. We look for the ECC value, correct? So when we see the ECC value, we look for the less than zero point 0.1 value. So when you have isolation below 15 dB, yes, you can achieve ECC value for less than zero point 0.1. If it is 10 dB, it will boost to zero point 0.3 or zero point 0.4 sometimes. So based on the MIMO feature, like we have seen that MIMO feature, to meet the MIMO requirement, the 15 dB is the threshold value where we should cross it. If it is 10 dB, we will not meet the ECC value. If it is below 15 only, we'll meet the ECC value. That is the reason 15 dB comes in picture. And like you have seen in the system, antennas are placed very close by. So sometimes and all antennas are the omnidirectional antenna. None of the antennas are directional. So all antennas are omnidirectional. So many antennas, at least for 4 6 antenna you will see in a system. So the isolation is become critical part for it. So we have to define that a spec, and spec is 15 dB. Yeah. Anything, or did I answer your question?
Yes, sir. Yes, sir.
Hello, sir.
Yeah.
Hello,
Yes, ma'am. Yes, ma'am.
sir. What will be the polarization effect in MIMO antenna?
Yes, it matters actually. It matters. Polarization matters a lot. So when we see the polarization laws in general, we say infinity, but in practical, it is close to practically we get 20 dB to 30 dB range. In general, 25 dB. So suppose one antenna placed vertically and one antenna is placed horizontally. Yes, we get the good isolation, and it benefit in placement. So the generally polarization, we always take a look, and we consider it, so we can place two antenna close by. So it matters a lot.
Okay.
So like if two vertical antennas are there, then I cannot place exactly next to each other. But if two orthogonal antennas, one is vertical and one is horizontal, then there is good chance that I can place it together and I can still achieve my isolation. And formula is, I think, cos square theta. So in relation with cos square theta, we can define, and practically it is 25 dB value if it is perfect orthogonal polarization, pure polarization, I can say.
Okay, sir. Thank you.
Sir, this is Anup here. I have one more question actually. It's
Huh.
related to intelligent reflecting surfaces. Right. I just wanted to know what research is currently going on related to that use of intelligent reflecting surfaces in 5G or beyond 5G applications.
Uh, I'm not sure because I have not gone on this area. My work is not gone on those area, and my work is also limited on this side. So I'm not sure. Sorry, Anup, on that part.
Oh, okay, sir. Thank you. Thank you.
Yeah,
Like I just asked you.
yeah.
Sir, one more question by Mr. Narayan. Does
Okay.
back reduce efficiency in directional and
Please repeat again.
uh, does back lobe reduce efficiency in directional antenna?
Not see, efficiency and the front and back radiation all are different parameter I see, or I say we can call as an independent parameter. First of all, today what we have discussed together is more omnidirectional. We have not seen the directional pattern. All we look for the omnidirectional pattern only. Only for the millimeter wave application, we look for the directional pattern. So now, just to answer in general, the back radiation, I don't see it will. It is a loss of efficiency. It's a radiation going in other direction. You can control it and you can push it on the forward direction. That will be the in general we can say to boost the gain, to boost the directivity, but I don't see go back radiation is causing a drop in efficiency.
Okay, sir. Thank you.
Yeah.
No, sir. There are no questions in the chat box.
Okay.
Participants, if you have questions, you can ask. Otherwise, I will conclude this session here, and then I will stop the recording, sir.
Yep.
Maruti sir, I have one last question.
Yes,
This
please.
when we are talking about the fifth generation of mobile phones, generally we
Yes.
talk about MIMO array, that is massive MIMO antennas
Correct.
for the base station.
Base
So
station.
as per today's understanding, we can see that at the base stations we are applying antenna arrays, but
Yes.
in the handsets we are basically using multiple input, multiple output antennas, say of 2 elements or 3 elements or maybe of 5 elements. So at the handset or portable devices, number of antennas are 5 or 6 like that. But in the base station, there is an array of antennas, right? Am I correct with this?
Uh, in millimeter wave, this particular one, in millimeter wave, it's a array. In base station, it's a massive array. It's like 10 cross 10, 16 cross 16, or 20 cross 20 array. But in the handset kind of devices, we'll have a small array, 1 cross 4 or 2 cross 4 or 2 cross 6, not more actually. So in general, we have 1 cross 4. That is the trend I'm seeing in the millimeter wave in the handset kind of devices. So here also there is array only for millimeter wave, but in case of other application in the below 6 gigahertz, it's a single antenna with MIMO feature. But in 5G is, 5G has two range. We call as a new radio NR, FR1, FR2. FR1 is below 6 gigahertz, FR2 is the millimeter wave. Okay, so FR1 in a system, it's a single antenna, and in base station it's a array, massive array again. In millimeter wave, it's a array in the small devices or handheld devices. In base station again, it's a massive array.
Thank you, sir. Thank you for this amazing presentation. It was very nice.
Hello, sir.
Thank you. Yes.
Sir, like as you told that there will be a large number of antenna at the transmitter. So at the receiver side, there will be only one antenna or more than one antenna for
No,
5G.
no, no, no. You see, in general, I'll tell you, in any 4G, 3G, 5G, any way, if you see the let's say today's what we are holding our phone, we have one transmitter and two receiver. As I said, transmitting is not much challenging part, but receiver is more challenging. So suppose somebody say no, you have limited space for antenna, then I will prefer one transmitting and two receiving, because while receiving I receive very low level of very low signal level or signal to noise ratio in my system. While transmitting, I can boost my increase my power level. I can do many things. I have more control basically. So while receiving, it's a more antenna. While transmitting, it is less. So today in 5G, I'll say you we have two transmitter and four receiver. See here, this main antenna is transmitting also, receiving also. Also, this aux or diversity is only a receiving. In 5G, there are two. One is transmitting and receiving both, and one is only receiving. So two transmitting and four receiving in the 5G case.
Okay.
Yeah, I think that's it then. Yeah. Thank you all for your time. Yep.
Yes, sir. Thank you. Thank you so much, sir. On behalf of the organizing team, the institute, and all the participants, I thank you for sparing your valuable time and your insightful, thoughtful lecture on antennas for 5G systems. Thank you so much.
Thank you all.